exam point of view. One or two properties will ask for exam. Weightage will be around 8 to 10 marks questions from this topic. So let us see what are the closure properties of regular languages. So first of all, try to understand what is a closure property. If a set of regular languages are combined, using a operator. So try to understand the student using an operator, then resulting language is also regular. So suppose set of regular languages are combined using an operator. As I told you in the introduction class or pre-video of this module, so there are three operators plays important role. The plus, union, concatenation, closure. Those operators you are combined it, still resulting language is also regular. That is what we are going to proving in this video. So what are those closure? So first property is called, there is union, intersection, complement and difference. So there is a one more property is reversal and Kleene closure, then concatenation, homomorphism and inverse homomorphism. So here it is, these two are very important. Sometimes they may ask in exam, and it is also very important, right? So this is different from Kleene closure. It is not a closure of Kleene, it is a closure. Okay, now let us prove all of this. Properties. So we'll go with the first property. Regular set are closed under union, concatenation, Kleene closure. Right, proof will be like this. I have taken two regular set L1 and L2 if R1 R2 regular expression. Right, if R1 plus R2, that means is a union, it denotes L1 union L2. With respect to regular expression, you have to write R1 plus R2. With respect to the language, you have to write it like this, L1 union L2. So L1 union L2 is also a regular language. And there is a, with respect to concatenation, R1 dot R2 denotes L1 dot L2. So L1 dot L2 is also a regular. Then R1 star denotes L1 star. So L1 is also a regular. So now, so what is the conclusion in this property? So this is, the first property is union, second property is a concatenation, third property is a Kleene closure. So from this it can be proved, as you have seen this also in a definition of regular expression. Whenever two or more regular set combined by using a operator is also a regular expressions. So we have combined two or three expressions, still resulting this is regular. Right. The second property you'll see, that is a property number 1. Regular set are closed under complementation. What is the statement of this? If L is a regular set over the alphabets sigma and L subset of sigma star, then its complement L dash is equal to sigma star minus L. Whatever the string is generated by sigma star will difference with L. So what that language will not be exist. That is called as L dash. So I have to do this. I have to prove them. Given L is a regular set over the alphabet sigma, then there is a DFA. How do you represent DFA? DFA by M pi tuples. M is equal to Q sigma delta Q naught F, accepting L is equal to L of M. So whenever it is accepting that language, and they have to write it in this format, L is equal to L of M. Consider another DFA. M dash is equal to Q sigma delta Q naught F dash, where F dash is equal to Q minus F. Therefore, M1 and M dash differ only in their final state, differ only in their final states. Final state in M dash is a non-final state of M and vice versa. Right? So how do you represent that in a state diagram of M and M dash are same except the final state? The state diagram of M and M dash is remains same except the final state. The final state of M will become the non-final state in M dash. Right? So then if you see X, suppose X is belong to L of M dash if and only if and only if this is if and only if delta of Q naught comma X is belong to F dash. Then if and only if delta of Q naught comma X is belong to Q minus F. So what is F we are writing? F we can write it, F dash is can write it Q minus F. That is what we are writing here. That is in place of F dash I am writing Q minus F. That means the delta of Q naught comma X is not belong to F. So because it is belong to F dash, it should not belong to F dash. It is belong to F dash, it should not belong to F. And finally, that word, X word is not belong to L. In other way, X is belong to L, X is belong to L, then X is also belong to sigma star minus L. Therefore, L of M dash is equal to L dash is equal to sigma star minus L. So now complementation, it is complementation now, it is just a minute, 1 minute. Right, we have done this by using a DFA. This is very important property. You can you can expecting for your exam, main exam, and also to use those to prove some of the complement language by DFA. Right. So now, therefore, L is a regular set since it is accepted by DFA. So again, one more property is intersection, which is also closed under regular set. The statement is like this: if L1 and L2 are regular set, then L1 intersection L2 is a regular. Proof will be like this: the L1 and L2 are regular sets given, they have given it here L1 already, it is there in the statement. Then you can take L1 dash and L2 dash a regular set by property. We have proved it by property 2 in a previous slide. So L1 dash and L2 dash is a regular set. Then L1 dash union L2 dash is a regular set. It is also proved by property number 1 in a previous slide. And if I take L1 dash union L2 dash whole dash is a regular set by property 2, right? So L1 intersection L2, because when you are taking this, then you can use the De Morgan's theorem, then you can get L1 intersection as a regular set by property 2, right? So now, so note L1 intersection L2, it is also L1 L dash union L dash 1 union L2 dash union is O dash by De Morgan's theorem. Proved by DFA, L1 is a regular set, there exists a DFA. M1 is equal to Q1 sigma 1 delta 1 Q1 F1 such that L is equal to L of M1. L2 is a regular set, there exists a DFA. M2 is equal to Q2 sigma 2 delta 2 Q2 F2 such that L is equal to L of M2. Right? Proved by DFA, continue like this. So I've done this through DFA. So you have taken, as usual, there is a definition of DFA. I have written that each one of them it is a Q, as there is a two DFAs are there, Q1 cross Q2, such that P1 comma P2 it is state such that P1 belong to Q1 comma P2 belong to Q2. Then you have to write it like this: delta P1 comma P2 is as taken input A. You can split like this: delta 1 of P1 comma A, delta 2 of P2 comma A. Then Q naught is equal to Q1 Q2, because there are two states, so two final states in with respect to two languages. Then if obviously there is a two final states, F is equal to F1 cross F2. We can write it like this: F1 comma F2 is belong to F1 minus F2. Sorry, F belong to F1, F2 belongs to F2. We show that what is that L of M is equal to L of L1 union intersection L2. Then you can take this statement. Here it is: X is belong to L of M. Then if and only if delta of Q naught comma X is belong to F, then what is Q naught? The Q naught is Q1 comma Q2. In Q naught it's you have to replace by delta of Q1 comma Q2 of X is belong to F. Then delta 1 of Q1 comma X, delta 2 of Q2 comma X is belong to F cross F1 cross F2, right? So then this can be belong to past state is belong to F1, second state is belong to F2, then X is belong to L of M1 and X is belong to L of M2. Then finally can take what is L of 1, L of M1, what is L of M1, L, what is L of M2, L2. Then how do you write this? X is finally belong to L1 intersection L2. So you can write it like this, hence the proof, hence the proved, right? So with that is the most two important properties had been discussed in the previous slide. Now let us move to the other closure property, or else regular languages are closed under set difference. I'll make it little simplify. We observe there is L minus M is equal to L intersection M complement. So closed under intersection. This is already we have learned it. Okay. And also closed under complementation. This is closed under this is a intersection. Second one is a complementation. This is a difference. Therefore, so we have proved this by the closed under intersection and closed under complementation. Then what is that? L1 minus L is a set difference. Therefore, L minus M is also regular set. And you have to take one more property is called reversal. Reversal is a very important property. Please take down it. Keeping in mind it is a make it star also in your notes. Reversal of string W is denoted by WR. Right? How do you write this? W is equal to 0 0 1 W over R is equal to 1 1 1 0 0. Reversal of a language is L power R, the language generated by reversing all strings in L. Language generated by reversing all strings in a L. Right? Okay. So now I'll write theorem will be like this. If L is a regular, then L power R is also regular. If L is a regular, L power is also a regular. How do you prove that? We can prove by using a regular expression. Let E be a regular expression for L. The given E, how to build E power R? So what is the e power r? Is a reverse of that given expression. If e is equal to epsilon phi ra, then e power r is also a e. Induction. Every part of e, that means it is a, can be in only one of the three following forms. F is equal to f1 plus f2. When I reverse it, f is f power r, f1 power r, f2 plus f2 power r, then this is also a regular expression. When I reverse it, this also it will be remain same. When I reverse this string here, f2 r power, it is remains same. So this, if you can reverse, you will get the same thing. So this also proved by some regular expressions, right? With this, then once you have seen that reversal operation, then you have to stop this video at this moment. We have learned all this concept, all the properties, 5 properties, and next few more properties we'll be discussing in the next pre-video. So at this moment I'll stop, and also you have a doubt, definitely more or less are all theory. Here it is, here and there some definitely you will get the doubt. We will be discussing in detail in the class, and whatever the doubt are there in this video, please take down those doubts and keep raise it in the classroom. We'll discuss over there. Thank you.